Hello again everyone, welcome back to ptet.chemistry channel. In this video, I'll continue this section B tutorial on section 10.6, which is on carbonyl compound, aldehyde and ketones. With this section B kind of question, we are given three statements or three options, of which the choice A, the multiple choice A, it covers 1, 2 and 3, relevant to what they're asking. B is 1 and 2, C is 2 and 3, and D is only 1, being relevant to whatever they're asking. Straight into this question. So which statements about the reaction sequence are correct? So sometimes it can be quite hard looking at structural formula to imagine what happened. The best way of thinking about it is draw it out and see it for yourself. Okay, there's nothing better than drawing it out and seeing it for yourself. So there's a OH at the end there. Preferably they will have put the HO at the end, but you will have noticed the carbon form 4 bonds at the CH2OH, CHOH, because carbon form 4 bond, we don't show hydrogen bonded to the carbon in a skeletal formula. This is a CHO aldehyde. And they give you that pyruvic acid, which is CH3CO, COOH. And they give you that lactic acid, which is that with OH, and the carboxylic acid. So looking at that sequence, what do we have? That is the ketone, alright? So that is the ketone. What we have now is it has become a secondary alcohol. I don't like that highlighting. Anyway, so what has become now is this is a secondary alcohol because the carbon with the OH is bonded to two other carbon. So this ketone has been reduced because going this way is oxidation. This has been reduced because this carbon gain hydrogen. Gain of hydrogen on the carbon is defined as reduction. Okay. And there is a secondary alcohol because the carbon with the OH is bonded to two other carbon. A secondary alcohol, well, I should check number 1 first. An aldehyde is oxidized to a carboxylic acid. Well, you have that aldehyde there, CHO. This is your carboxylic acid. You have a hydrogen here. So aldehyde can be oxidized to carboxylic acid because this carbon can lose that one hydrogen and gain oxygen. So there is oxidation. Aldehyde is oxidized to carboxylic acid. This compound also contains a secondary alcohol. And this is a secondary alcohol. So what happened with this secondary alcohol is this position becomes this is secondary alcohol become ketone. So there is oxidation because the carbon with the OH has lost the hydrogen. Okay, so there's no more hydrogen there. You have lost hydrogen, that is oxidation. Alright, so it's a bit unclear what happened to this OH, but it gives you this, and that is not the interest of our reactions. What we're interested in really is whatever they have given us, so I won't talk too much about what they haven't told us to do apart from the normal alcohol, aldehyde, ketones, carboxylic acid kind of chemistry. So since all three are correct, that's option A. Moving on to the next question, we have this steroid. Steroid is an intermediate compound obtained during the synthesis of blah blah blah. We use it in the treatment of breast cancer. So a lot of drugs that look complicated, they all come from simple steps, and drugs have different because the bigger they are, the more is the potential to have many different functional groups. For instance, this one here is a ketone. Alright, I hope you can identify that being a ketone, and this is a secondary alcohol, and this is also a secondary alcohol. The carbon with the OH is bonded to two other carbon. Now, when we look at this OH, we look at this carbon with this OH is bonded to two other carbon, secondary alcohol as well, yeah? So we don't have primary alcohol, so when you say it can be oxidized, yes, it can be oxidized by acidified potassium dichromate 6. So that is dichromate, which is Cr2O72 minus. There's chromium plus 6, which is orange, to a carboxylic acid. Is incorrect because we don't have primary alcohol. 2 is wrong. You only have one option, which is D. That means only one is correct. And we know one is correct because we have that nucleophilic addition reaction between a ketone. Okay, so probably shouldn't have to write that down. So the ketone can undergo nucleophilic addition with HCN and you need NaCN or KCN catalyst. Okay, and by default, since number 2 is wrong, only 1 is correct, and number 3 should be wrong as well by default since 2 is wrong, but I'm going to check number 3. It says you react with Phalanx. Phalanx solution is that blue colored solution that is used to test for, it's got copper 2+, so it will form that brick red PBT if aldehyde is present. So it's a test for aldehyde, and we do not have aldehyde here, we have ketone, so it will not react. Okay, it will not react with Phalanx solution. So again, it confirmed that 3 is wrong, 2 is wrong, only 1 is correct. But you always check for number 2 first. Number 2 is wrong, you could move on by convincing yourself that D is the option. In the next question, how can we increase the rate of reaction between ethanol and aqueous HCN? So this is your nucleophilic addition. This is your case study in AS level and also A level chemistry. So basically it's asking you about rate really. When you increase temperature, you can increase rate of reaction because you can change the Maxwell-Boltzmann distribution, which you know because you have done rate of reaction topic in A level. And of course you also affect collision frequency. So there are 2 different things. Yeah, if you irradiate with UV light, it's not going to affect the rate because that is for free radical substitution reaction. And if you do introductory organic chemistry, you know the free radical substitution reaction involve homolytic fission. Homolytic fission give you radical, whereas we are dealing with nucleophile and electrophiles, which are charged species, not radical. So number 1 is automatically wrong, and because 2 is correct, 1 is wrong, you're left with option C. I'll just check option 3 just to make sure. Indeed, we use a small amount of aqueous NaCN as catalyst. In fact, if you remember your mechanism, if you have ethanol, which is an aldehyde, delta plus carbon, delta minus oxygen, the first CN minus that attack the carbonyl is not from HCN, it's from the nucleophilic completely charged Na plus CN minus. Okay, so it's actually from the catalyst, and then you form the oxy anion intermediate and you will get CN, and then your reactant will give you the source of the H plus, and then you will get the OH and the CN, which is the nucleophilic addition product. But looking at what happened here, this will give you that thing again, and that is regenerated. So essentially we might not get the exact same CN minus as we started with, but we do produce CN minus in the end to give us to regenerate us back the NaCN catalyst. Alright, that's why it's a catalyst, it's not used up. Alright, but it will speed up the rate of your reaction. In this next question, so this is vitamin C. So based on this structure, I hope you can see this is an ester. It is not a ketone because you always have to check on either side. Alright, a ketone would be carbon and carbon on either side of the C double bond O. This is an OH bonded to alkene, and I don't want to talk too much about this functional group because you are not, it's not something that you learn exactly in A level. It's not as simple as like OH bonded to a carbon, which is bonded to 2 other carbon. It's not as simple as that because you got a double bond there. Yeah? It's not a diol as well, because when you have a di, it is a diol, but it's not like diol formed from alkene when you have normal alkene. Here you have alkene still. Instead of focus on this OH is bonded to this carbon, and this carbon is bonded to 1 other carbon and 2 other carbon. So this is a secondary alcohol for that, whereas this one is a primary alcohol because this OH is bonded to this carbon, which is bonded to only 1 other carbon. Alright, it decolorizes aqueous bromine. Yes, it's got a carbon-carbon double bond, which will give you the electrophilic addition. It's a mechanism which is a case study again in your A-level chemistry. So you can catch my topical playlist specifically on organic chemistry mechanism, where I outline every single mechanism that you're supposed to know in A-level chemistry. Okay. Now they're all your case study there. Solubility in water, that is precisely correct because you can OH forming hydrogen bond with water. Just simply stating it is not enough. Make sure you know how to draw it. Draw one molecule of this, draw one molecule of this, show the lone pair on the oxygen here, or show the lone pair on the oxygen here, label the delta plus and delta minus, the delta minus and delta plus, and then show that they can form hydrogen bond with water, and therefore makes them soluble in water, right? So these are the kind of thing that the theory level paper really like to ask. The next thing, it says it reduces Felling's reagent. So Felling's reagent is a test for aldehyde, where it can oxidize aldehyde, and then the aldehyde will reduce the Felling's reagent, alright? From copper 2 plus, which is blue, to copper 1 plus, which is copper 1 oxide, which is a brick red precipitate. But you have an ester, you do not even have any aldehydes at all. So number 3 is wrong, so it's just option B, which is 1 and 2. So this is the last question in this 5-question series of this section B on 10.6, which is on carbonyl compounds. We have glyceraldehyde, so this is the structure that's been given for us. If you have watched my other tutorial videos, you will know that I'm a big fan of using skeletal formula because it's elegant, it's fast, and it's something that students, A-level students especially, should be very accustomed of drawing, even though it's not given the question. All right. So I'm going to sketch out the skeletal formula, HOCH2. I have a CHOH, hang on. So there's a CH2, and then I have a CHOH, and then I have an aldehyde. So I don't show the hydrogen bonded to a carbon because that's the way skeletal formula is. I don't show the single hydrogen there, but it's got an OH, it's got an aldehyde, it's got a CH2 because carbon form 4 bond, 1 and 2. So the 2 hydrogen are not shown, and there's the OH at the end there. So this is glyceraldehyde, and it contains a chiral carbon. So which one will react with glyceraldehyde? You want to produce the organic product without. Okay, so if we check number 2 first, as that's the normal case we do, we check for number 2 first. So this is a reducing agent. This is an aldehyde. This is a secondary alcohol because the carbon with the OH is bonded to 1 and 2 other carbons. So this is secondary alcohol. This is primary alcohol because the carbon with the OH is bonded to 1 other carbon. So alcohol itself is not reduced any further by reducing agents such as NaBH4. Instead, what happened is the aldehyde was oxidized from primary alcohol. So what you could get is you could get a primary alcohol back again by reducing this aldehyde. And this looks different, but in actuality this is a CH2OH. This is also a CH2OH. So you can hopefully see that this CH2OH is the same as this CH2OH. So this is not chiral because the carbon there is not bonded to 4 different groups of atoms. This group and these groups are the same. Okay, so this product is not optically active because it does not have a chiral center. So they want to produce an organic product without a chiral center. So this is what we want because sodium borohydride gives us a product with no chiral center in the product. Okay, so be very careful of how you read the question. If we then try to oxidize it, so we reflux it with acidified dichromate 6. Dichromate 6, this is potassium dichromate 6. It's actually K plus 2 of them. Therefore, you have Cr2 or 7,2 minus. This is the orange color chromium plus 6. This is oxidation number. This is the ion itself. And there is oxidation. So primary alcohol will be oxidized all the way to carboxylic acid. Aldehyde will be oxidized all the way to carboxylic acid. Secondary alcohol will be oxidized to ketone. So what I'll get is, I'll get a ketone, I'll get a carboxylic acid, and I get a carboxylic acid there as well. So again, hopefully you can see that you have a CO2H and you have a CO2H. Again, oops, and by the way, you don't even need to worry about chiral carbon, because now this is a sp2 carbon. This is a carbon sp2 with 1, 2, and 3 sigma bond on this carbon, therefore 3 bond pair and 0 lone pair. This is a trigonal planar 120-degree. Carbon sp2 cannot be chiral because the carbon is no longer bonded to 4 different groups of atoms. So this product does not have a chiral center. You want a product without chiral center, so this is it will give you a product with no chiral center. How about if I react that with Tollens reagent? So Tollens reagent reacts with aldehyde. It oxidizes the aldehyde. It's basically silver +1 with 2 ammonia. So it's a complex of these Tollens reagent. It will specifically oxidize aldehyde without oxidizing the alcohol. So the primary and the secondary alcohol remain the same. It's actually in an alkaline condition. By the way, such as sodium hydroxide or potassium hydroxide, so that you never really get the carboxylic acid, you always get the salt of it, unless you acidify it in the last step with excess acid. Regardless, I hope you can see that you actually have different groups. This is a CH2OH, this is a OH, this is a carboxylate, which could become carboxylic acid if you add in excess acid to get rid of the hydroxide, the alkaline condition, which is part of Tollens reagent, by the way. And this thing is chiral, so it has a chiral carbon, and therefore that is not a product that we want. According to the question, you want a product without chiral center, so only 1 and 2 are correct. There must be option B there. So that's the end of this 5-question series. I hope this kind of topical MCQs would have been far more useful than the full paper tutorials. And ideally speaking, you should be going through more topical MCQs, because I actually cover quite a lot of theory within each topical MCQ video tutorials. And that's because the distractors, the wrong options, present very good scope for discussion on what is actually the correct chemistry and what might seem very confusing. So thank you for watching, and don't forget to click the button on the bottom right to subscribe to the channel, and do share the channel widely with all your friends, chat and study groups, your juniors and seniors, relative, and whoever else is doing the A-level chemistry. Okay, see you in the next tutorial video. Thank you for watching.